All right, howdy. So for the second example, what we want to do is we want to look at this cube. Okay, we have a metallic cube, and we want to figure out what its surface charge density is. So that's the charge on the surface. Now that's going to be all the charge. So remember, for our um, metal, if I put two charges in the center here and here, they'll move off in opposite directions. So that I'll have one charge here and one charge here, and they'll actually probably migrate to these corners, so they'll be as far away from each other as possible, right? So that's what they'd like to do. But as we add more and more charges, they'll keep being as far away as possible from the other ones, and the old ones will move as well and stuff like that. So that you'll have you'll have your charge spread along your object. Sounds good so far. On top of that, for a sphere, this would be completely uniform, because for a sphere it doesn't really matter, it's completely symmetric. In this case it's not completely symmetric, so you'll see that more charge tends to end up in these points since it can get farther away from things, right? And that's actually a big problem if you're making something that's supposed to be electrostatic. You want to get rid of the points because those big charges mean it's easy to discharge from those spots, and that reduces the amount of charge you can actually get on this square, on this cube. So we're pushing all the charge off to the edges of our cube, right? So that's little plus signs all over there. And there are hopefully, I missed one. There should be 10 little plus signs on that cube. And so that's going to be all over. We want to look at the average surface charge density, because there are these confluences, I guess, or these more highly charged spots on your cube. Basically, by using the average, we just make it easier, and that's the reason why we're using the average. Let's see. So if we want to do some pre-analysis on this, we say charge is equal to the density. And this is the two-dimensional surface charge density times the area. So it's just on the surface. And the surface is the surface of this entire object. So it's this and this and this, and the other three surfaces. So that's what we're going to have to worry about going forward. Let's see. The area, like I said, is equal to 6 times the area of one of these guys, which is the square of the length, so L squared. And we can do that. That's pretty easy. 6 times the square of 1 centimeter, which is 0.01 meters squared. Okay, so that's going to be equal to what? 6 times 10 to the minus 4 square meters, right? So that's what we'll use when we do our math, our mathematical analysis. So math comes up next. Okay, thank you. All right, so we've got this, and remember we just said this was 6 times 10 to the minus 4 square meters. This area of the cube, that's a surface area of the cube, technically, because that's the only kind of area I know that a cube has. If you know of other kinds of areas for cubes, well, tell me about them. All right. Next, we'd like to do sort of our algebraic analysis. Well, basically, what we have to do here is we divide both sides by a. Did I already do? Oh, I already did that in this thing. Okay, so that's our density, our surface charge density. And our charge here is 10 times 10 to the minus 6, that's the micro, right, coulombs. And the area is this other one we have here, 6 times 10 to the minus 4 square meters. I didn't check. This might be wrong. We'll find out. There was a little error yesterday when I did this, and then I never got a chance to come back to it. And I didn't check if OneDrive updated everything like I'm supposed to. So let's see. We can get rid of a 2 in this one. That's why it's 5/3. And we have minus 6 plus 4, right? 1 over 10 to the minus 4 is 10 to the 4th. So that's 10 to the 4th times 10 to the minus 6. And that's 10 to the minus 2 coulombs per square meter. And we're going to call that a number. Okay, 3 goes into 5 once, and then we have 2/3, so that's like 1.67, but we'll do 16.7 and put one of those over here, so we have 10 to the minus 3 coulombs per meter squared. Then we can just pretend it's 16.7 millicoulombs per meter squared. So we can use as many m's as possible. All right, so that is correct. And let's see if the answer updated, and it did. Okay, so good. We did update we did update the answer. I mean, sometimes it takes a while for OneDrive to get everything back together. So what did we do? Well, first we basically wrote our definition of the surface charge density, right? So we have various densities, right? So D1 was the line charge over the length, right? So if you had a wire, you'd get your density for that. D2 would be, oh, this is Q. Q over the area, like we just did there. So we're just looking at a surface. We could do that for just a plate. We don't need to have a cube. In this case, the surface of a cube is just like 6 plates. And D3 is the normal density that we normally think of. That's the total charge over the volume. So if we had a cube or something, that's the one we'd use. So this one we care about the surface, so we use this guy here. The surface area of the cube, again, is 6 of these little plates. So we have one plate here, that's 1 plate, 2 plate, 3 plates, and then 4, 5, and 6 that are behind there. And after we've got a value for that, and we've got a value for this, we just do the math until it's done. All right, thanks. Bye now.